a little bit faster than the speed of sound, maybe 600, 700 feet per second. They don't move that fast. And they are also a very complex motion. They involve a lot of rolling motion. But that complex motion takes a lot of energy. So the nice thing about surface waves is they don't last long and they don't go far. They die out. So they're going to have most of their impact close to where the earthquake actually occurred. And they're not going to last long, away from that. They frequently produce a phenomenon known as ground roll. Big explosions will do that too. It's really cool. But essentially, that energy makes the ground move like water ripples, like waves on a pond, like ripples on a pond. You can actually see the ground roll like waterways. Now, if you have buildings, there's a reason why we don't build buildings on water. Okay, they can't stand the motion. Okay, we build boats for that. Surface energy can seriously damage structures and cause a tremendous amount of damage. Which is a good thing. They don't go very far. They don't last long. Any questions? Well, so we have an earthquake. What are some of the first things you're going to want to know about it? Location. Location. That is the first critical information. Location. We have two ways to describe the location of a quake. You have the focus, otherwise known as the hypocenter, and you have the epicenter. Scientists are going to be a little more concerned with focus. Search and rescue relief efforts and other people are going to be more interested in epicenter. Focus is the region, the place, the point on the fault that broke. It is the source of the energy. It's where that stress was released. The location, region, spot, on the fault. I'm not walking home over there. I don't have any handprint on my pink shirt. So location, region, spot, on the fault. Where those rocks finally broke loose of each other. And that focus can be very close to the surface. It can be practically at the surface if your fault comes all the way up. It can be a few miles deep. It can be up to 300 miles deep. There's a depth limit to how far faults can go, because the deeper you go into the earth, what happens with temperature? And it gets hotter. And what happens is, if you have broken rocks that get hot, they get hot enough to flow back together again, so they kind of heal that breakage. And once that's not broken anymore, it can't move. So there's a depth to how far faults can be. If you have a really deep focus that you can feel at the surface and cause damage, that was a powerful quake. If you have even a small quake, if it's close to the surface, it can cause a tremendous amount of damage. Because the closer it is to the surface, the more of that energy is going to go to surface energy rather than through the earth. It's kind of like, you know, you have a stick of dynamite. Now you can bury the stick of dynamite, 30 feet underground and blow it up, and you'll see the ground go. Or you take that stick of dynamite and you just, put it on the patio in the backyard and run like hell. Because that comes up, it's going to come, wow! It's going to take out the tree and the garage and the car and all the windows in the house are gone. So, if it's closer to the surface, most of that energy is going to go to the surface. And so even if it's a small quake, if that focus is close, it's going to cause a lot of damage. Seismologists, earth scientists who study earthquakes are going to be very concerned with focus. We keep track of that. We monitor, we plot, we record where that focus happened, on what fault, at what depth, at what time, how big. We record where and when and how every single time because we're looking for patterns. We're looking for patterns of behavior along that fault because hopefully somewhere in that pattern is a predictive tool that can help us predict when the next one may occur. Tracking that information can also be very helpful with knowing what type of earthquake and what size and what power of earthquake we may expect in the next one and how to be better prepared for it. So we're going to track that all the time. Epicenter. This is going to be the location that's on the surface, on the ground. You stand on it. It's going to be the area on the ground that's located directly above the focus. I gotta get the research. I gotta walk all the way over here, all the way back again. Things I do for you people.
We're very grateful.
I know, you should. I cannot get upset today because Cheryl brought in this ginormous basket of candy and I'm eating half of it for lunch. So it's the epicenter. So that was the phone call. No, that was something far more stupid than that from higher up in the administration. Our ground surface directly above focus. Search and rescue teams are going to want to know where's the epicenter. Typically, and this is a very general rule, damages are going to be worse at the epicenter. That's not 100% true because it depends a lot on what types of rocks are underneath you. But in general, the worst of it is going to be at the epicenter. So, your search and rescue teams need to know where do we need to be dispatched to first. Where are there going to be people most in need of being dug out, being rescued, being evacuated? Who's going to need, the clean water and the electricity restored and all that? Who's going to need that work first? City planners, city engineers, civil authorities, street maintenance, city maintenance, they're going to need to know where was that epicenter. Where are we going to have the most damage to our pipelines and our subways and our roads? Who's going to need public service restoration sooner? What do we have over in that area? Is there a school over there? Is there a hospital over there? Is there a business district? What kind of help are they going to need? What needs to be fixed or repaired or restored first? And it's going to help for planning for the future. Looking at what types of damages resulted and why. Maybe looking at changing some zoning restrictions, some building codes. Deciding where to build new structures or not to build new structures. What level of earthquake code tolerance buildings may need in that area. Insurance companies are going to want to know epicenter. They're going to want to know the types of damages that resulted so they can change and amend their policies that they offer to people for earthquake insurance. Earthquake insurance, like any natural hazard, is a separate rider. You have to pay for it separately. You can get earthquake insurance in the state of Ohio. the odds of getting a quake big enough to impact Ohio in a very disastrous way are low, and in light of newer research, they're lower than we had first expected. We may have dodged a bullet. I mean, nature could surprise us, but I'm banking on I'm not. Are there any questions? I'll talk about our earthquake risks when we look at earthquakes and plate tectonics, probably on Tuesday. So that's location. You gotta know location. If you keep track of earthquakes, especially big ones, and quite honestly, big ones are the ones you hear about most often because they make the news. People die, people get hurt, things fall over, weird stuff happens. Oh my gosh, did you hear about this thing? Yeah, so that's the big ones are the ones that get advertised. But keep in mind that earthquakes happen 24/7. Okay, there is the NEIC. That's the National Earthquake Information Center. You can Google it. They update the earthquake list every 3 hours. And it tracks earthquake activity around the globe. And there are literally hundreds and hundreds of earthquakes every day. You don't hear about most of them because either they are in very remote areas or there's nobody living, so who cares? Or they're on the ocean floor. Again, who's going to know it's 5 miles underwater? Maybe the fish was upset, and that was about it. But, and others are so low in magnitude that they don't cause any appreciable damage. And they may show up in local newspapers, but they'll never make national news. But happen all the time. In addition to knowing their location, you need to know how bad was it. There are 2 ways that we scientists describe the severity of earthquake. We track it by magnitude. We track it by intensity. Magnitude is an estimate of how much energy was released. An estimate of how much energy released. And there are several ways that we measure this, we scientists. Intensity looks at severity from a different perspective. Intensity is an estimate of severity based on the type and amount of damage that resulted. Magnitude, for scientists, is more kind of looking at what the heck the Earth just moved was. And intensity is more of a, okay, how can we build this better so it doesn't do that again when the next one hits? So one's a little more science-backed, and one's a little more maybe engineered-backed. So we use them both. Magnitude, there are 2 scales that are pretty common even today, although we're trying to phase the one out. But you've probably heard of it, and that's the Richter scale. We also have the moment magnitude scale. That's what scientists use. Richter came up with the magnitude scale in the 1930s or so. Scientists don't use it much anymore today, but it's still something that's often at least familiar with the general public. So it may also still be used just to have a way of conveying information to the general public and the general media. But it's not really used that much. It's a quick, down and dirty, good ballpark estimate that you can do right off of the incoming data. So it gives you at least a starting point of getting an idea, a feel for how bad the quake was. Moment magnitudes are a lot more common nowadays. They're calculated globally for just about every quake. It involves a much more complicated mathematical equation. I'm not putting it on the board, you're welcome. And in that equation, you have a lot more parameters, a lot more variables. It takes into account the physical strength of the rocks involved on the fault. It takes into account how much of the fault moved, how long was it moving, how far did it move. It takes into account a lot more of the actual physical attributes and character of the motion that was responsible for releasing the energy. So there's a lot more factors involved. It tends to be considered a much more accurate measurement. Typically, moment magnitudes calculate out to about the same, maybe a little higher than most Richter. Both scales are all scales actually, are typically going to be on a scale from about 1 to 9. Some scales start at 0. Moment magnitude, I think, goes to 9.5, 9.8. You cannot get 10. Okay, let's just start with that. So good Hollywood, good Sci-Fi Channel, and all that stupid stuff. Cannot get 10. No magnitude 10. Oh my gosh, what did I? No, you're not going to get a magnitude 10. 10 is, on any magnitude scale, is physically not possible. It's not physically possible for rocks to collect enough stress to produce a 10. It exceeds their physical ability to do that. So now we have had 9.6s. We have had 9.8s. We've had 6.5s that are bad enough, so that we will not get a 10. It's a small consolation. Anyone see that movie this summer, San Andreas? Anyone see that movie? Everything you saw in that movie? No, not really. They're advertising the DVD now for that movie. You don't feel it on the East Coast. No, you won't. Don't get me started. So we have these scales roughly from 1 to 10, and they will use Arabic numerals. That's what we call basic numbers, 1, 2, 3, 4, 5, 6. Those are Arabic numerals. Arabic numerals. Intensity is what's on the Mercalli scale. And Mercalli divides this scale around about the same time, 1930s, 1940s. And still used today. It's referred to as the modified Mercalli because building techniques, structural design, engineering has changed a bit since the 1930s. And so it's been modified to accommodate more modern structures and more modern building styles and whatnot. Mercalli scales range from 1 to 12, but it uses Roman numerals. Like your 18 wheels of a big rig, one, I, maybe that's stupid stuff. They count to 18 in Roman numerals. Okay. So Roman numerals. This is very handy because when you make a map, you can put magnitudes and intensities on the same map and not get the numbers confused with each other. keeps them separate, so you know visually which number is the magnitude and which number is the intensity. So now, if we look at magnitude, the Richter scale, again, it's a quick estimate from the seismogram. Seismogram is that record that will be formed as the recording machine detects the motion of that ground. Now, very simply, a seismograph machine recording instrument starts with a platform. That platform, that base, is somehow attached to the ground. It's attached to the wall of the building, it's attached to the foundation, it's attached to the ground, it's attached to the floor, it's attached to the foundation, it's attached to the ground. In some cases, you actually dig a hole, and we put the instrument in the hole, so it's in contact with the ground. And from it is supported a roll of paper, because you have to be able to record. And also we have suspended over the paper from a spring a stylus. That's going to be your pen, it's going to make all the marks. Your stylus is a spring. And that's going to make your, it's going to make your seismogram.
What kind of similar way you used to do like within the shop or like when you speak, like and the vibrations and that?
Yeah. Or like EKG or yeah. It's recording the shaking, recording the vibrations. Seismogram translates as earthquake record. Now the interesting thing is here, because you'll see this in movies, that just makes you want to slap people. But, you'll see that, it'll be like, oh my gosh, oh, there's the earthquake. Okay, the pen is not moving. The pen is not moving. It's like on a spring. The spring is an inertia dampener. It's like a gyroscope. It suspends the pen and it absorbs the motion. So it maintains the pen in a fairly constant position. The pen does not move. Now, the roll of paper that's connected to the base, that's connected to the building, that's connected to the ground, that moves. Why? Because the building's moving. And why is the building moving? Because the ground is moving. I gotta stop making me sick. So it's fascinating to watch these things go off, because when you're sitting there looking at it, you can swear that pen is just, but it's not. You don't feel it because you're moving with it. It's the whole building that's going this way underneath the pen. It's creepy. It's really creepy. Who here has a cat? Has a cat, knows of someone with a cat, has experience with a cat? Small birds are good for this too, but you got to be very careful. You got like a parakeet or a bungee, and you got the bird. It's like a connection with what? Move it around real carefully, and its head will stay in the same place. But you can move the body to the bird. What are you doing? Just don't do it really fast. So you get a cat, you get a friendly cat. He'll kill you otherwise. And you bring it up under the armpits, right? And you're holding it so the legs are hanging. Oh, this is a good kitty, good kitty, right? Move the cat like that, and front, side, side. And again, their head will tend to stay in the same place. They'll be like, what are you doing with me? Yeah. That's kind of what's happening. Everyone's going to have to go to the shelter now and find a cat. Wow. Oh, yeah, she's right. What's she doing? Okay. So, that's ready to see your birds. No. Don't want that one. Don't want that one. But that's what's happening with that spring. It's keeping that pen still. It is the building and the paper roll that's moving underneath it. So that seismogram comes up. For Richter, you can, of course, P wave is first. P for primary, it's fast, it's going to get there first. S wave is going to come in later, it's slower. That's going to give you a time difference here in seconds. Time difference. It'll give you an amplitude. Amplitude is the highest or the most pen swing. The biggest mark that was made.